3 external reviewers. Okay, all of them got really good marks, but of course we could only in the end find 4, and these 4 projects will be presented today. And more or less, this is it. Just a bad joke. Just, yeah. You know, these are the trigger projects. But when we circulate this in administration, trigger was not a familiar name, and they understood tiger. And if you know Spanish, trigger means gatillo, a small cat, and a tiger. It's a big cat. So, and the protagonists are the IPs of the trigger projects. Okay. Who starting? Yourself?
The one in the first
Okay.
row.
So there are 4 projects, 2 of them with a single IP and 2 of them with 2 IPs, which was possible. So you decide who talks first and who second and who third and who fourth. Okay. The floor is yours.
Okay. Go ahead. No, dale a compartir pantalla. No. ¿Tienes el ratón, solo?
Well, hello everyone. Good morning. I'm going to give a brief overview about our trigger project. That it's just starting now, so I won't present results, just the state of the art and the main objectives of the project. And the project aims to develop a plasmomechanical platform for high precision monitoring of the bacterial growth before the cell division. The PIs are myself, Ferran, and Sergi Brusel, that is not here, but is here in Seoul. So let's go ahead. Well, first of all, why is it important to measure the bacterial growth with precision? So it's critical at different levels. Firstly, in fundamental biology studies, of course, but also critically in diagnostics and also in environmental monitoring. In particular, it is very critical in the determination of the antibiotic susceptibility of bacteria in clinical isolate from hospitals. Antimicrobial resistance is an emerging health problem, and it's nowadays considered one of the main health threats worldwide, and it is expected to increase in the near future. Well, the bacterial growth cycle of a typical standard bacteria is quite simple. It's composed of the elongation phase, in which the bacteria grow in the longitudinal axis of the cell only, and then it becomes to cell, which is the division. Here we can see, well, don't look at the title of the video, we can see a little bit the process. If you can see, the bacteria first become longer, which is the elongation phase, and then maybe it's barely visible actually, but yeah, maybe you have to imagine. Yeah, they elongate first and then just become to cells afterwards. This process is repeated over and over and over time, and it becomes a big colony of bacteria. Well, again, so we can define the division time, which is the time the cell needs to become 2 cells through the process I showed. And this division time is constant for a specific type of bacteria and under specific growing conditions. Well, regarding the methods to measure to monitor the bacterial growth, there are many different methods to measure the bacterial growth after many division cycles, which are based on assessing the change in biomass, mainly normally, but only microscopy is able to measure the cell elongation over time with precision. So this is a matter of time. In this plot, we can see the division time of some examples of typical bacteria. In the case of fast-growing bacteria, in the left, for example, E. coli, they can have a division time of 20-30 minutes, less than 1 hour, which is more or less fast. But there are many bacteria that can, in which the division time can last for days or even weeks. So that they grow very slowly. They grow very slowly, and it is really a problem that delays the time to answer when you measure the growth. For example, when testing antibiotics against these bacteria. For that reason, in recent years, many different technological approaches has been proposed to tackle these issues. There's new technologies for monitoring the bacterial growth are based, for example, in microfluidics, electrochemical sensors, optical sensors, fluorescence, mechanical sensors, Raman spectroscopy, etc. There are some techniques that are like very sensitive, other less sensitive. But the main issue of these techniques is that they measure indirect parameters that are correlated to bacterial growth, but they don't measure directly the bacterial growth. And apart, sometimes they have low sensitivity as well. So, motivated by these issues and inspired by the idea that the plasmonic near-field interaction is very, very sensitive to small changes in the interparticle distance. Sorry, maybe I should say that, I mean, plasmonic near-field interaction is a coupling of the plasmonic fields between plasmonic nanostructures that is especially strong when the plasmonic nanostructures, for example, gold nanoparticles, are very, very close, closer than the diameter of the particle itself. So in this plot, in the right plot, you can see how the absorption spectra of a dimer to distinct gold nanoparticles changes as a function of the interparticle distance, with a very, very high sensitivity to small changes in the gap distance. In this plot, it goes from 1 to 5 nanometers, and the color change is quite high. For example, plasmonic near-field interaction has been exploited in the recent years in the development of plasmonic rollers that are able to measure the changes in the distance among biological molecules like DNA, or for example, in developing mechanically tunable plasmonic nanoantennas, which are normally composed of 2 plasmonic elements that change in the interparticle distance, and you can measure it with an optical spectroscopy. So in summary, the objective of this TRIGGER project is the development of plasmomechanical technology for high precision monitoring of the bacterial cell elongation using a simple spectroscopy measurement. So we propose the use of soft, gold-coated soft plasmonic nanogap antennas to measure the bacterial elongation. We foresee to this aim, we foresee 2 different approaches. One approach, which is the approach one, consists on confining the bacteria between dimmers of antennas. And the approach two involves attaching the bacteria on the top of an array of plasmonic antennas. Well, here we have to keep in mind that the performance of our system will be affected by both the mechanical sensitivity of the system and also the plasmonic sensitivity of the system. The mechanical sensitivity mainly depends on the aspect ratio of the antennas and also on their stiffness. Briefly, the mechanical sensitivity will be proportional to the aspect ratio of the antennas and will be inversely proportional to the stiffness, which is expressed by the Young's modulus of the material. Also, the plasmonic sensitivity is critical in our technology, which will be mainly determined by the gap distance between the antennas, which should be less than the diameter of the antennas, to allow the near field coupling, a strong near field coupling between the antennas. So the project includes the work package one, which involves the design and manufacturing of the plasmomechanical platform. It will be done by nanoprint lithography. First, silicon master will be fabricated by electron beam lithography, will be coated by a gold thin layer, and then it will be replicated in a polymer which is called off stoichiometry thiolin, OSTE, which is very interesting for this application for many reasons. On the one hand, it has a low Young's modulus, close to PDMS, a bit higher. And also very interestingly, it has complex surface chemistry that presents thiol groups in the surface, which may facilitate the interaction of the polymer with the gold that has been deposited in the silicon master. In addition, it can be processed by photolithography, allowing a scalable fabrication of the devices. The work package two involves the studies on the functionalization of the devices to allow suitable bacterial adhesion, which is critical for our application. And then the work package three, in work package 3, we will evaluate the performance of the system in measuring the bacterial elongation and its potential application in antibiotic susceptibility testing. And that's all from my side. Thank you for your attention.
Any question?
Question for that, but I don't know if here the topic, like we can discuss this. Why it's so important the replication of the bacteria for the antibiotic? The thing that you explained at the beginning is with the antibiotic.
Yes, it's important because the standard methods for determining the antibiotic susceptibility of bacteria are mainly based on growth parameters. So they put bacteria a control sample without antibiotics, and then with the antibiotic you want to test, and you compare the growth. And it's limited by the division time, as I said before, because you need to wait for at least several hours to have a result. So, yeah. Yeah.
It's about the device that you should take, so so in your slides, I think I saw that some dimensions like 200 nanometers.
Yeah, 200 nanometers. It's the.
So you need to make this pattern. Then you need to do the molding and unfolding of this structure.
Yeah.
I mean, I didn't get nicely with how easy will be to make these in the dimensions. So I mean, I didn't conceptualize very nicely the experiment.
Yes.
Maybe with the, I mean,
Yeah, that's a very good question. Yeah, this is, this is just the first approach, but really we are now preparing the first run for the first trials. But I think, yes, this is the most difficult step probably to make this replication from the silicon master to the polymer. The thing is that if the polymer is very soft, like this one, it might be difficult to maintain the distance between the antennas and so on. So it's not easy. And another option is making it on silicon, of course, making like the silicon antennas, which will be less sensitive, mechanically sensitive, but might be more stable. We'll see. It's really, it will be empirical, probably.
In fact, I was trying to find out what you have just answered. My question was, what are the challenges you are anticipating? So I think you have just answered.
Yeah,
this
well,
question.
there are many challenges, but first the technological challenges regarding the fabrication of the devices. Actually, just the fabrication of these kind of devices may be a challenge itself. Yeah.
The bacteria are stable in the surface or removed in the surface?
That's why we will use chemical functionalization of the antennas to immobilize the bacteria. Yeah. So
And this will affect the result also, because
it might affect, but the thing is that there are chemical linkers that they are normally used for bacteria adhesion on surfaces that they do not affect, at least so much, the metabolism and the growth. Yeah.
Okay, so next one, Esteban. Tienes que abrir aquí el archivo e ir al Zoom para compartir. Sí.
Yes, okay.
Sí.
Well, hello, everybody. Thank you for coming. I'm Esteban. I would like to present my trigger project that is entitled Manufacturing Vertical Silicon Nanowire Devices to Extend the Performance of Future Circuits and Systems. This is the goal that we want to achieve. It's a vertical pillar, and we want to transform it in a MOSFET, in a vertical device. Okay. And now I would like to present how we will achieve this. But first, I would like to present a little bit of the state of the art and the context where we are working on. Usually, the semiconductor industry is working usually in planar devices, okay, always using horizontal dimensions. But since FinFET implementation, the vertical topology arises. But it seems that the future for 10 nanometers or 5 nanometers technology nodes, vertical dimensions, vertical devices will be the most promising option. And then we will shift from the 2D layouts to the 3D layouts. So this will be involves a relevant change on the design circuits. Moreover, the IRDS predictions in 2020, they predict that beyond 2028, one option to reduce the device dimensions, the area footprint, sorry, of the circuits is stack the devices one over the other. In this case, they say that you can put the P devices over the N. So then you will reduce it to the half of the circuit. Then also IMEC is working on that. The most common and the most well-known work is the nanosheets devices, where they put lateral nanowires one over the other. With this, they improve significantly the performance. And more recently, they are working on 4 sheets and CFET. CFET is complementary FET, where they place the P devices and the N devices over the P devices. So with this, the vertical structures are becoming more relevant for the nanoelectronic
for the nanoelectronics. We have some examples. The right one, this one is a classical CFET where planar devices are put it one over the other. And this is an IDM contribution. The bottom right is a bottom left, sorry, is a IDM contribution where they implement a CMOS inverter by using lateral nanowires, but they put the P nanosheets, the P nanosheets on the bottom and then nanosheets on the top. So this is a very vertical structure and is a really interesting device for the future. But nothing lies for everything, for all time. And it seems that as we reduce the technology node, there will be a limit, and the limit is the contact pitch, the distance of the contact pitch. And it seems that the vertical devices will be who will substitute the planar devices, the planar implementation. For these vertical structures are very interesting for the semiconductor industry. So we are going towards this field. Then my work, or this project is focused on manufacture a vertical nanowire and transform it to a MOSFET, vertical MOSFET. This is the idea. The vertical devices presents lower energy consumption, presents better performance in terms of delay reduction, a relevant reduction of delay on a CMOS inverter, for instance. It presents lower parasitic elements and also less leakage current in the device. There are different methodologies to manufacture this vertical device. One more conventional can be the EBL, the electron beam lithography. But in this project, we will explore another one that is the colloidal lithography plus math. Math means metal-assisted chemical etching, where nanospheres will be placed first in the wafer. Later, a noble metal will be deposited. We take out the nanospheres, and then we have this mesh of the metal layer. Usually, it is implemented by using gold or silver, and then by using a specific solution that is made by peroxide and fluoridic acid. You oxidize the region below the metal, and then with the HF, with the fluoridic acid, you remove this oxide layer, and then the metal layer is going down, and the pillars arises. Unfortunately, gold is not CMOS compatible. And what we want to explore in this project is we want to explore a CMOS compatible option. And for this, there is some references that make the metal-assisted chemical etching by using titanium nitride. And that's idea is what we want to explore. Okay. So there are many applications for the vertical devices, radiation sensors, neuronal circuits, biological sensors, solar cells. Also are interesting for some other projects that belongs to this call, and so on. So we have a lot of applications for these vertical structures outside of the nano devices. So the objectives. First, develop a CMOS compatible technique to obtain high aspect ratio silicon picos. Two techniques will be explored, MATHE and RIE, just a conventional RIE. Then another key issue of this project is the doping, because we need different regions of doping just to make that our pillar is a transistor. And this we will explore two different options. The first one is using ion implantation from here, from our institute, from the CNM. And other option is epitaxial growth. To do this, we will take advantage of ASTEM program and NFFA program. And we are talking with several institutes just to try to achieve collaboration with them and manufacture this epitaxial growth. And finally, we want also to integrate everything and make that this vertical pillar becomes a MOSFET. To make this, we will take advantage of our previous experience in a European project called Ions for SET, where we integrate a vertical pillar as a single electron transistor. So we have experience on the integration, but we have to develop a lot of work on the other two tasks. These are the tasks to be done. As I mentioned, doping, etching, and final integration will be the main ones. There are a lot of processes to analyze and a lot of experiments to do. TCAD simulations to observe the optimum device dimension and device characteristics, and the other one that I have already presented. Well, as I mentioned before, the integration will be adapted from IOS for set, and the rest should be developed. These are the work packages. Okay, first pillar obtained by reactive ion etching. Another work package is obtaining the pillars by MATHE, vertical doping, and finally the simulation. So these are the first results that we obtained from our TCAD simulations. Okay, these are the structures simulated with different dopings, but we want to analyze other parameters, other device parameters as diameter of the pillar, channel length, gate electrics, materials, and so on. So we have a lot of work on this, and we have a lot of experience on this kind of simulations. Also, we have made the first studies on colloidal lithography. These are the first studies. I remember two paths to analyze, to make experimental work. One based on reactive ion etching and the other based on the MATHE. For the reactive ion etching, we are using polystyrene nanospheres with a 60 nanometers diameter. With this approach, we only have to deposit these nanoparticles, and then by a reactive ion etching, we will achieve the pillars. It's easy, it's more direct, it's more easy. More direct, more than easy. And for the MATHE path, we are using silicon nanospheres, 120 nanometers of diameter. We are using silicon nanospheres because later, when we deposit the metal, this deposition method achieves high temperatures, and the polystyrene spheres will die. For this, we are using silicon nanospheres. Then, by peeling, we take out the nanospheres, and by MATHE, we should obtain or we should achieve the pillars. So these are the first results, very preliminary results. So we have deposited properly the nanospheres, 60 nanometer nanospheres, and we obtained the first, we can say something like pillar, but we can say that this is a pillar, but it should be optimized, significantly optimized. Okay, this is tilted 45 degrees, just to see the pillars. For the MATHE path, okay, we deposit, we metallize the nanospheres, we make the peeling, and we make the first proof or the first tentative of MATHE. But more studies should be done just to optimize. Also, just a risk mitigation measure. If we are not able at the end to achieve the correct pillar, the proper pillar, we will do some EBL lithography just to achieve this pillar and be able to implement a MOSFET. Also, we have designed the process flow. I will not come in detail, but it's a long process flow where we have contemplated the different steps. Okay. This is the final goal of this project, to achieve the implementation. Also, we have the next steps are obtain the pillar height. So we have to optimize RIA and MATHE, and manufacture the multiple doping structure. As I mentioned before, IM implementation made here in our clean room, and epitaxial growth by collaborating with ASTEN and FEFA partners. In case of do not obtain a correct multi-doping structure, one option is to implement the device in a junctionless option. Okay, then we avoid and we need only a highly doped silicon region. And this project is a seed of a future European project that we are starting to write, and we have to present at the end of this month. We have the consortium almost done, and we are trying to write this proposal and be successful in the future and try to use this for the future projects. Also, I don't want to finish this presentation with acknowledging my research team, Alberto de Moral, Borja Sepúlveda, Arnau Ramos, and the advisory board, Francesc Pérez and Jaume Esteve. So thank you for your attention, and I'm open for questions. Thank you.
Wants to start?
Excuse me, so maybe you mentioned, but we didn't get it. Which is the height of the pillar?
100 nanometers. Yes, I forgot. The idea is 100.
100.
What centimeters?
100,
Repeat, please.
100 nanometers.
I saw in the presentation that the spheres are like randomly placed in the wafer. So how do you plan to have like scalable process? Because after that you need to do like the photolithography for metal and so on. How do you plan to do it like in a future step?
Yeah, this is the images that you saw is the first study is with the positivity in the first run, and we have to improve it this. And the other option is just to by EBL lithography make a region where only the nanospheres deposit. This is one idea, but first we want to prove the integration process.
For the system,
Yes, yes.
for the system integration, all the steps that you need are at CNM, or you?
Yeah.
Yes.
Yeah.
Even for this oxide in the lateral.
Yeah, we can implement by ALD.
And another question is, I think it's important the quality of the lateral surface of the nanoplasms.
Yeah, that's
we
a,
are trying to use a specific characterization of this surface.
yeah, this is one thing that we have to think about, because I agree with you that the surface, the quality of the surface is a key aspect on this, on the performance of the devices, and we have to think. And in fact, another option is the junction-less implementation. For the junction-less implementation, the current flows through in the center of the pillar, and then the surface is not so important than for the PN junction, where the current flows in the surface. But this is one thing that we have to explore. There are options as a there are processes as a sacrificial oxidation, that then you reduce a little bit the pillar, but then you remove the oxidant, and then the quality of the surface is better. This is another option.
Maybe you said that, but why are you using these 60 nanometers particles? I mean, is it critical the size, or is it just?
No, it's, the size. Our goal is to achieve very small pillars. Very small means 50 nanometers, something like that. I agree with you that maybe 60 is too risky for the first steps of this project, maybe, but it was the first nanospheres that we have, and we try to explore with this just to see if we are able to do it with 60 nanometers.
Okay, so thank you, Esteba. We move on to the next one. Whoever. And you have to share it on Zoom. No, porque estamos haciendo. Sí.
It's not visible yet. Okay. Great. So I will be introducing you to our project, Place, not to be confused to Climate. Since that we were playing Wordle the same day. This is a project together with Felix, who I think she's online. And yeah, the title is Planar All Carbon Electrode Diamond Dosimeter for radiotherapy, but it didn't get into the title. So many of you are familiar with silicon. Some of you are also familiar with silicon carbide, but not so many with diamond. So this is a mandatory introduction to the material. In terms of material as a detector, diamond is some advantages because, well, if you don't have access to cooling, and you don't need it because it has a very high thermal conductivity. It has a high displacement energy threshold. This means that it needs more energy. You need more energy to remove one atom from the lattice than say silicon. So this makes the diamond more radiation hard than other alternatives. The atomic weight is very similar to the tissue. This makes diamond so-called tissue or almost tissue equivalent, which means that there's the dose to detector and the dose to medium, in this case tissue, conversion is almost one. You can see the plot on the right that I got from somewhere. and this is important for radiotherapy planning. Drawbacks: high energy, high electron hole pair generation energy. So you need, again, in this case, you need more energy to generate an electron hole pair, which is making out your signal. So you have lower signals. And yeah, but I think it's widely known that it's not a cheap material. So just to for reference, one sample, few millimeters by 3 millimeters, is of the order of 1,000 euros. So if you want to have a guess where the project money is going to, be my guest. Yeah, so how a typical traditional diamond detector looks like. So it's basically a solid state ionization chamber. You have say a diamond, your material, in this case diamond, like sandwiched by metal electrodes with which you apply the an electric potential. And when ionization radiation gets into the diamond, it generates electron hole pairs, and to collect the charges. Actually, the current is induced by the drift of the charges. So this is a technicality, and you get a signal. So the idea again is to use diamond as material for dosimetry. In particular, flash radiotherapy. This is it's relatively new way of radiotherapy. It benefits from using ultra high dose rates deliveries, which have been proven to reduce the toxicity in cancer treatments, meaning it affects more the cancerous tissue than the healthy tissue. So, but problem is ultra high dose is very high. High doses in very short time, less than 200 milliseconds even. And there you have the reference of from conventional radiotherapy. So you need a fast and radiation hard dosimeter. So in this case, as I mentioned earlier, we focus on using diamond. It is critical to achieve better than 1% dose linearity. This is a requirement for clinical applications. And that's the commercial devices already achieved that, but I think there might be some room for improvement by removing the metal to reduce the metallic electrode, to reduce the multiple scattering from the metal. And by doing so, by removing the metal and replacing it with graphite, which is the main idea, is you improve also on the tissue equivalence, because you're removing a high set mass, material from the device. Yeah, the goal is to get the diamond with graphitic contacts for radiotherapy dosimetry. This is also called the all carbon diamond detector approach. This we're not the first ones to try this, but typically people use this femtosecond laser graphitization to replace the metal, which has been proven to work. And there's even possibility to make 3D columns into the bulk out of graphite. The problem is that's slow. That's slow for large fraction. So basically, the bottleneck is well, the laser movement, alignment, and it's a very convoluted process. It can get very convoluted, and of course, here we'll have a 1 million euro femtosecond laser. So here we explore other approaches to produce graphitic electrodes. Here I'm naming some graphitization by catalysis. You deposit nickel, and nickel acts as a catalytic material, and after annealing, you get graphite on top of the diamond, on the surface of the diamond. Then pyrolytic photoresist film. This basically you do pyrolysis on the photoresist resin. This has been shown actually in a previous CNM talk by Sophia, and that was done on silicon carbide. And we can also explore other ways of graphitization that we can do in the clean room, like graphitization by indentation. All of those are scalable processes, and you can imagine there exist diamond wafers, and in those diamond wafers, one could do many iterations of the same device. This is I'm showing here a polycrystalline diamond wafer, 13 centimeters, and on the right is a monocrystalline diamond wafer, quote unquote. What we want to get is ohmic contacts, and to assess the quality of the contacts from these different fabrication processes. We can do Raman spectroscopy to see how much graphite diamond is left in the fabricated electrode. We are planning to do transmission line method structures to measure the contact resistivity and so on. And of course, we are starting with samples available in-house, but the final idea will be to get a prototype dosimeter out of electronic grade diamond that we have to get. So notice again, sample size is small, so it's challenging for the lithography. So for the time being, we're using mainly laser writing for photolithography. So the final product from here will be a prototype dosimeter. And then comes the prototype characterization. So first, we are going to mount, the plan is to mount the device into ceramic encapsulation. This is compatible with clinical QA, and then we measure a charge collection efficiency, dose rate linearity, which is which should be our figure of merit. Both in the radiation laboratory, since we recently got the license to use the new X-ray tube, and if everything goes well, we can also test it under rain conditions in, say, Sevilla, and the National Accelerator Centro Nacional de National Accelerator Center. This is the summary. So we want to produce this planar or carbon electrode dosimeters for radiotherapy, because diamond is a radiation hard material, is fast. It's a fast detector. There's potential to remove inaccuracies by removing the metal layer, and replacing the metal with graphite makes it more efficient. So we want to produce those devices with a scalable process available here. And then we test the prototypes and the laboratory and accelerators. And of course, if all goes well, we can even extend the project to produce a final product. And that's everything from my side. Thank you.
Ivan, any question?
Thank you, very nice proposal. I have two questions. First one is that you mentioned that you take profit on the high thermal conductivity of diamonds, because you don't need to cool the detector. Please discuss on that, because do you have large amounts of heat to extract?
Okay, so no, that's okay. Here, actually, in this case, it's not. We're not going to hit it's not going to go for very high. So this is just an extra characteristic of diamond as detector, which is actually useful because I have a background on particle physics instrumentation. So that's also like you always put that. So you have to excuse me. So, but then of course this can be used also for others.
And second question, how do you contact your graphite layers? Do you need at any moment to make a wire bonding or something like that?
Yeah.
And
so
yes, how will you manage that?
Yeah. So I ideally know wire bonding, but so far wire bonding, yes. Some groups have been able to wire bond on graphite. Actually, I think yeah. So in the second row of images, this dosimeter done I think in Italy. The wire bonding, they were doing it on top of the graphite from the surface, which for what I heard is challenging but possible. And then how to remove that, that's out of the scope of this project. That's important to think about, I think, in the future. So right now we are dealing with a diamond sample of 0.5 millimeter order of magnitude, but commercial diamond detectors are very, very thin. I think they claim micrometer.
I was talking about the graphite.
Oh, the graphite layer. I can, well, for the ones that we are producing, I cannot tell you for sure because we have to produce it. For that, I will be surprised if it's more than 1 micrometer. I will have to check in the paper.
Where do you do the pyrolysis here? In the...
Yeah, it's we have one oven here in the clean room that has been used for that, for what I've understood. So, but I cannot tell you which machine exactly. It's basically an oven.
It's a curiosity, maybe just
Yeah.
a bit question, but when you say that it's tissue equivalent, are you taking into account the water of the tissue?
Yeah.
Or only the carb?
Okay, so there's a like equivalent. So there's the atomic mass equivalent of tissue is 7.66, depending on which tissue you're talking about, and the one for water is also very close to that, and so yeah, so basically carbon being atomic mass 6 is very close to that.
So the absorption is only determined by the atomic mass, and the density doesn't have any role.
I think after you take into account the density, everything evens out. Yeah, but that's not a stupid question.
Thank you.
Anything else? Okay, so thank you, Ivan.
Thank you.
Oriol Viñó, last but not least.
Good morning, everyone. Oriol Viñó. I will present this trigger project entitled Oxide Reliability in Silicon Carbide, or SiC. First, I will do a brief state of the art and present the main motivations of this project, and then to present the main objectives and the expected outcome. Well, our final use case are power MOSFETs, silicon carbide power MOSFETs. In this way, silicon carbide outperforms silicon in most of the main properties. Here we have specific on resistance for in respect to the breakdown voltage, where we can see that silicon carbide has a gain of 3 orders of magnitude respective silicon. A factor 10 can be attributed to the depletion region width, and the factor 100 due to the doping concentration. But there are other aspects, such as the semiconductor critical temperature. In this case, in the intrinsic concentration, if the intrinsic concentration becomes higher than the doping concentration, there is a risk of thermal runaway. In the picture, we can set in other terms, this is the capacity to block a voltage respective in the junction temperature. Here we can see that for 1 kilovolt, for example, silicon can block this voltage at around 200 Celsius, where silicon carbide could be capable to block the same voltage, 1 kilovolt, at around 1,300 Celsius. Then why we are not working at higher temperatures? Well, there are other limiting factors, such as packaging, and besides, the oxide is another limiting factor in silicon carbide MOSFETs. Performance and resistance improvement is key in power semiconductor devices. In silicon carbide MOSFETs, most of the main defects which have impeded their commercialization until now are now solved, such as micropipes or stacking fault, but there remains other issues compromising their reliability, such as robustness under short circuit, robustness under avalanche mode, packaging, bias thermal instability, gate oxide robustness, and the intrinsic diode robustness. In this project, we will focus on the gate oxide robustness and the time-dependent dielectric breakdown, TDDB. All right, you can see the TDDB with a probability of failure of 63% versus the oxide electric field applied in a component, in several components. These are commercial ones. Well, now let's describe the first objective of this project is the reduction of the time consumed during TDB test in up to 2 orders of magnitude. Such tests are high time consuming in the order of more than 1,000 hours and are only or mainly performed by manufacturers for qualification purposes. Such data are not usually available to final user, and we would like to propose a customized test to perform to final hardware engineers to perform a fast TDDB test, and to extrapolate results to their final application temperature and voltages. Well, and in the picture, we can see the TDDB respective to the unapplied gate voltage. We can see different points which are more or less aligned. And usually these points are extrapolated using the thermochemical model. And we can see that the TDB at 30 volts should be around 10 million hours. Well, but what happens if we would like to faster the test? At one point, the acceleration factor of the thermochemical model changes. Then this could lead to an overestimation of the lifetime. What we would like to do to faster the test, we would like to propose a novel physics-based methodology coupling these two physics behavior, and to extrapolate the result, doing tests in the red region above here around 43 volts, and be capable to extrapolate that to the nominal voltage of the application. Well, and this methodology, we would like to assess this methodology at different temperatures. Then the final user should be capable to perform this test in around 100 hours and to have an estimated lifetime for their application temperature and voltage. Well, second objective relates to the physical signature of the TDB test. We would like to perform lock-in infrared measurements complete with SEM failure analysis. Well, at left we have a microscope image of one device which have failed after a TDB test, and at right we have their corresponding thermal image. If we couple both images, it should be possible to locate the failure. and using same analysis, we would like to inspect and found the failure, to analyze the weakness of the component. Fortunately, here we don't observe the failure, and we expect to do another attempt increasing the current compliance of the current source, or exacerbating the defect, also increasing the current of the failure to exacerbate the defect, or by means of other inspection techniques. This is the third objective, which is to reproduce by means of decade simulations the current behavior. We will take into account the Fowler-Nordheim phenomena and the impact ionization. In this way, Fowler-Nordheim is important, especially in SIG, in such tests, because the lower barrier height, as well as the fact that the oxide is submitted to higher electric field, because its thickness is lower than in silicon devices. We can observe in the picture on right that around 43 volts, it starts a deviation of the Fowler-Nordheim current model. And this corresponds to the change on the slope we have seen before, and also agrees with the picture at left. We see around 50 nanometers, which is the typical thickness of the oxide in power MOSFETs. We have that around 9 megavolts per centimeter, the impact ionization phenomena is triggered. Then this fact agrees with the starting of the deviation of the Fowler-Nordheim, and also with the change on the slope. Well, the expected outcome of this project is first provide a new methodology for faster testing, facilitating customized reliability experiment design. Also, we will use transversal competencies of the institute, such as SEM analysis, perhaps atomic force microscope, optical electrothermal characterization, TCAD analysis, and so on. We expect to collaborate with Esteve Amat in the experiment design, and Marta Fernandez with inspection techniques. And the knowledge transfer will be assured by the realization of TFM and divulgation activities. And we expect to obtain at least a scientific conference contribution. This is all for my side.
Uriol, any question? Francisco?
I have two questions. In addition to the fact that silicon carbide will have a different work function with the silicon oxide, what are differences are already reported of these silicon dioxide layers on silicon carbide in terms of breakdown voltages?
I mean, there are a lot of things involved, because breakdown voltage here it was around 40 volts. You refer to that, and in silicon it's much higher, but the applied electric field is different, and I think I'm not answering your question.
Okay. And the other point is, which metal are you using in the experiments or in the devices?
No,
the structures. What metals are you considering to be used in your experiment?
The first experiments were based on commercial MOSFETs. Then,
Okay, so you will know.
yeah.
My question is also related with this. You are using commercial transistors. You will not fabricate specific pieces structure or some processes.
We would like to manufacture CMOS capacitance to analyze the TDD. We are still in the first stage, but we have to do. We like to do that also in commercial MOSFETs for then in the perhaps we will do this manufacturing in CMOS, but it's under development.
Well, if there is nothing else, or any question for the previous ones you now have, we can finish the session. This is no, there isn't. And this is it for today. Thank you for coming and sorry for the delay.